Good afternoon, everyone. My name is Mohit, and I'm here with Ashish, and we are going to talk about building a distributed continuous integration platform using Mesos and Docker. At eBay, each project and team gets a dedicated Jenkins instance, and each Jenkins instance runs inside a dedicated VM. Now, to give you a rough idea, we had thousands of these VMs running just Jenkins, and when we measured the resource utilization on these VMs, we found that it was very low. In fact, it was less than 5%. And the reason the VMs were idle most of the and the reason the utilization was this low was because the VMs were not doing anything most of the time because the Jenkins was not building code all day long. So we were looking for a solution that would help us improve the utilization of resources in our cluster. Also, at eBay, we have a polyglot application platform. We have stacks for Java, C++, Python, Scala. Also, each of these stacks require a specific toolchain to perform builds. Also, the applications that are done in these stacks can either run on RHEL or Ubuntu. And when you have these two variables in picture, you can imagine how hard it is to not have version conflicts between the software dependencies. So this really made the management and maintenance of the boxes that were performing builds really hard, and we were also looking for a solution to fix that. And here's what we did. We figured that to fix these problems, we need to do 4 things right. First, we need to manage our resources more efficiently, and to do that, we chose the Mesos project. Mesos is a cluster manager that provides efficient resource sharing and isolation capabilities. Also, we needed something to execute tasks on these managed resources, and we chose the Marathon project for that. Marathon is a Mesos framework that allows one to launch and manage long-running tasks on Mesos. Also, it comes with a REST API, which makes it really easy to integrate that with your existing PaaS solution. Also, we needed something to execute builds in a distributed fashion, and for that, we chose the Jenkins plugin, the Jenkins CI, which clubbed with the Jenkins Mesos plugin, which allows Jenkins to act as a Mesos framework, and Jenkins can now run the build jobs as Mesos tasks in the cluster. Also, we wanted something to package our application and the dependencies in a format that was portable, self-sufficient, repeatable, and we chose Docker for that. The bottom part of the slide gives you a high-level overview of the architecture. On top, we have Marathon that we use to launch and manage the long-running Jenkins masters. In the middle, we have Mesos, which is managing the slaves and is also assisting Marathon to launch tasks on these slaves. And at the bottom, we have the slaves where the tasks actually run. Now, if you'll notice the color coding is there to highlight the fact that these slaves can either run a homogeneous set of tasks or a heterogeneous set of tasks. For instance, slave 1 is only running Jenkins master. Slave 2 is running just the Jenkins slaves, whereas the slave n there is running a web application and also a Jenkins master. So all this is made possible with Mesos and Docker. So now let's look at how Mesos advertises resource offers and provisions tasks. So blocks on the extreme right are the Mesos slaves. Blocks in the middle are the Mesos masters. And only one of them is primary at any point in time. And the blocks on the extreme left are the Mesos frameworks. The resources offers travel from right to the left, whereas the tasks get provisioned from left to the right. Let's take an example to understand this better. So in step number 1, we have the slaves, a bunch of slaves which comes up and they starts advertising resources to the Mesos master. So the slave 1 is advertising, let's say, the 4 CPUs and 64 GB RAM. Slave 2 is offering 4 CPUs and 128 GB RAM, and slave 3 is also offering some resources. And in step number 2, the Mesos master is now offering these resources to the connected frameworks. Now, the Marathon framework wants to launch a task, and the task requires certain amount of resources to be executed. And those characteristics are, if you can view that, it's 2 CPUs and 512 MB RAM. So what Marathon do is, in step number 3, it accepts one of the offers which Mesos provided, and it sends the acceptance along with the task information that is required to launch the task. And in step number 4, Mesos actually goes on the slave 1 and launches the task number 1. Now, the task number 1 is already running on the slave 1, so it does not have all the resources that it earlier had. Now, we also have another framework in the cluster, which is the Jenkins framework. And Jenkins also wants to, let's say, perform a build, which is signified by the task number 2 here. And since Jenkins is also a framework, Mesos is sending it the resource offers as well. And this time, the offers that it gets, specifically in the offer number 1, it will get the less resources because slave number 1 is already running a task. So it has lesser number of resources than it had originally. So Jenkins also wants to run a task, so it accepts one of the offers and sends the acceptance along with the task information, and Mesos then launches that on slave number 3. I mean, it's a lot of information for one slide. I mean, these slides will be available online for review later. Now that we understand how Mesos is advertising resources and provisioning tasks, let's look at how we can use the Marathon framework to launch a long-running Jenkins master. So on the extreme left, you have the Marathon framework, which wants to launch a Jenkins master. And like I said earlier, it's a Mesos framework, so it's getting resource offers from Mesos. It accepts one of the offers which matches the criteria, sends the launch command to Mesos master, which in turn forwards that to the chosen slave. Slave in turn launches a command executor, takes the launch command and actually executes it, which brings up a Jenkins master instance. And it listens on a port that is dynamically acquired using Mesos. Also, this Jenkins master framework is using the Mesos plugin, which the Twitter folks have written, which, like I said earlier, makes the Jenkins master a Mesos framework so that it can launch the build jobs as tasks in the Mesos cluster. So now let's look at how that happens. So like Marathon, Jenkins also is registered as a framework, and it's getting resource offers from Mesos master, and it wants to launch a build job. So it again sends the build launch command to the Mesos slave, and the command executor comes up and runs the Jenkins slave process on the slave box. And once the build job is completed, the build artifacts are given to the Jenkins master, and then the slave process stays there for a while. And after the timeout, it just goes away. And that's the key point, because in the earlier model, the Jenkins the resources that were acquired by Jenkins will stay there for a long time, even if they were not being used. Whereas in this example, we are using a master-slave architecture where the master is not using a lot of resources because it's just doing the orchestration, and it's being used by developers to view their builds and what happened and look at the console logs and stuff like that. So it doesn't require a lot of resources to run. So in fact, when we run it, we only give it like 0.2 CPUs and 256 MB of RAM. Whereas the actual build is performed by the Jenkins slaves, which are ephemeral, which are not long-lived, which just comes in, performs the build, and then just goes away. So the advantage of that is you can now share your resources in a more fair manner with other people, or the other tenants in your cluster. So yeah, so now I'll hand it over to Ashish, who will talk more about Docker.
Thanks, Mohit. So far we have seen how we use Mesos in combination with Jenkins, and we were able to reduce our utilization. Now, the other problem that we wanted to solve is what do we use so we can package all our application dependencies and make the final deliverable that Jenkins produces a lot more portable, and we can scale up, scale down very easily. So let's first cover just the base requirements of why we chose Docker. Now, eBay uses a variety of OS flavors. It uses Red Hat Enterprise Linux. It uses Ubuntu. So deploying a large Mesos cluster in combination with these two OSs involves a lot of automation, tooling, monitoring that needs to be built around that is specific to these OSs. So that is a hard problem to solve. Now, the other plus point of Docker is that we want to isolate our dependencies, basically silo it, because one Mesos slave can be used to run several Jenkins build jobs. So we really want to silo all our build jobs. One can be a Java build job, the other one could be a Python one, Scala one, so that's where Docker's containerization comes into play. Now, the third factor is that Docker allows the host OS to be independent of whatever OS that it is running. So what that means is that my Mesos slave can run Ubuntu, whereas my Docker container can be a Red Hat container, simply because the Jenkins job requires some RPMs to be installed inside of it. So that keeps it fairly independent. Now, the other big question that comes up always is, why are we using Docker in Docker? And before you guys give me a weird look, let me clarify one thing, that we are not actually running Docker containers inside a Docker container. All that we're interested in is doing a build, a tag, and a Docker push. So essentially, we are producing a Docker image as a byproduct of the Jenkins build. So the advantage of this, as we will see in subsequent slides, is that this eliminates redundant CI build dependency downloads, which is basically like downloading the JDK, downloading Maven. So every build job can have a different version of the JDK that it needs. So that kind of stuff. And also, Docker in Docker helps to enforce a heterogeneous Mesos slave cluster. So as Mohit covered before, the same Mesos slave node can be used to launch a Docker container, can be used for a bad job, can be used for a Jenkins build, pretty much anything. We don't discriminate between what kind of job we want to run on a Jenkins slave. Now, let's cover the basic use case at eBay. When we embarked on this project, we were basically told that this is what we need to accomplish to support the existing functionality. So if you look at the leftmost block, that's your Jenkins master. Every developer or project would get one. Now that Jenkins master essentially is bringing up a Red Hat Docker container, inside which our typical Jenkins slave process would be spawned. That slave process would do its job, and it would run maybe some C++ build or Java build, and then the final deliverable that it is uploading into our own proprietary package repository, which is usually a zip file, a tar.gz file, or even a WAR file sometimes. So it tags it, puts a version number of it, puts a timestamp on it, and puts it into its package repo. Now, the important factor, as you can see here, is that the Mesos slave is actually Ubuntu, whereas the Docker container is running Red Hat, which is very, very good for us, because then we can meet these varied OS dependencies. And all the application dependencies can be pre-installed inside the Docker container-based image. Now, as you all might know, Docker uses union file system layers, so we don't need to download the same layers containing, say, the JDK or Maven again and again. We can just reuse those layers if they're cached on the Mesos slave host. Now, this is the advanced use case. Why would we really want to use Docker in Docker? So it's pretty much the same flow. On the leftmost block, we have the Jenkins master. A developer would trigger a build, and the Jenkins master would launch a Docker container on some Mesos slave. The Jenkins slave process spawns up inside this Docker container, and instead of building a tar.gz or your vanilla Java WAR file, this Jenkins slave process is actually building a Docker image. So in essence, we are running Docker inside Docker. And that Docker image would again be tagged, version, timestamped, and put into a private Docker registry that we would host. So all the variables pretty much remain the same. The Mesos slave host can be Ubuntu or Red Hat, and a Docker container running that Jenkins slave job could also be Ubuntu, Red Hat, or vice versa, any combination that you want. Now, here is the final enterprise CI workflow that we came up with. So this is like whatever we discussed before this is the final picture. So if we start all the way from the left, we have the Jenkins master. The Jenkins master is basically a Mesos framework. It gets resource offers from the Mesos master. Its job is now to launch builds. A developer will just say, run my build every 3 hours or once every 24 hours. So the Jenkins master would tell the Mesos master that I have a build that I want to launch. It has certain requirements, this much CPU, this much RAM, etc. The Mesos master would then relay that to the slave whose offer met that request. Now, the Mesos slave, instead of using your standard command executor, which basically just spawns your standard process, instead now it is triggering a special executor called as a Docker executor created by Mesosphere. Now, what the Docker executor does is that it manages the lifecycle of a Docker container, as you can see there. So the Mesos slave launches the Docker executor. The Docker executor then brings up a Docker container within which that Jenkins slave process is now spawned up. Now, the Jenkins slave process immediately connects. It phones home. It calls the Jenkins master, and then it downloads all the build scripts that it needs to essentially run my build. Now, once the Jenkins slave process has all the scripts, it starts running it. And then the final deliverable of that build process would be a Docker image. So what's going to happen here essentially is every application in their Git repo, they would have a special Docker file. Now, if you're a Scala project, your Docker file would have a base container image that's specific to Scala. A Java project would have a Java Docker base image. And so every base image would already have everything like the Tomcat web server or whatever web server dependencies pre-installed. So that way we don't spend time installing them using apt-get and all that stuff. So depending on your project, that Docker base image would be used, that Docker file would be used to start building an image. The Jenkins slave process would build a WAR file or some binary that executes your application code. It would then insert it into that image while building it. It would add that file. It would package it up, and it would version timestamp it and push it into the private Docker registry. So now instantly, we have not only done our CI stuff, but we have produced a fully functional web app image container and pushed it into a registry that can be deployed immediately. Now, this Jenkins slave process, as Mohit mentioned previously, is that we don't keep it around forever. It usually lives for a short window of time. There's an idle timeout, after which the Jenkins master kills it off. So what the Jenkins master terminates essentially is that Docker executor. Then it kills the Docker container and everything inside of it, the Jenkins slave process and the Docker image. All the resources used by the entire chain of components is released back to Mesos immediately. So this makes it a very, very efficient system in which that when I have a job, I'm running something. When I don't, everything is cleared up, and those resources are used by someone else. Now, here's the initial build strategy that we followed based on a blog post by Jeremy Perezzoni from the Docker team. He described a way to use privileged mode to actually run a Docker daemon inside a Docker container. Now, initially, this was the only strategy available to us, so we went through with it. So what happened essentially is that we were, the Jenkins master, as you can see, it ran the Docker container. The Jenkins slave process spawned up inside of it. And that slave process was talking to a locally installed Docker daemon and a separate isolated Docker cache. And then the output of this process was the same. A Docker image was pushed into a Docker registry. Now, what this guaranteed us is complete isolation, even at the Docker level. That means that the Docker container that you're seeing outside is launched by a separate Docker daemon with a separate Docker cache, and whatever Docker-related stuff that my build job is interacting with, that is isolated within that container, full isolation. But there's two big drawbacks to this strategy. The first one is that the Docker daemon, first of all, privilege mode is not something we should be using very often. It's a security problem, because then you acquire certain privileges, you can mess up your host system. We really don't want to do that. And the other thing is that the I/O overhead of downloading and duplicating all the layers. So whenever you run a Docker pull to download your base container image, it could be several hundred megabytes in size. So imagine that every time I run a CI build job, that Docker daemon running inside that Docker container is downloading hundreds of megabytes of files and layers every time. So we really don't want that. It took forever to run a build job. And the other negative that maybe is being fixed now, but I haven't tried this experiment for a few months now, but what I observed is that the Docker daemon running inside ran a union file system, and that file system was mounted separately on the host server. You can't mount a union file system inside a union file system. So the Docker container that you're running has its own separate files on the host, whereas a Docker daemon running inside of it has another separate location where it puts its files. So once this Docker container is killed off, once the job is done, there's nothing to clean up the files that the inner Docker daemon created. So our disk usage went up and up and up. We didn't know what was happening. So we avoided this strategy entirely. So we worked with Jeremy, and he came up with a much better option, which is actually now in the public Docker documentation as well, which is, let's follow the flow. So on the leftmost block is the Jenkins master, same flow. It brings up the Docker container. The Jenkins slave process comes up inside of it. That slave process is now doing a Docker build and a push. But now we don't have a Docker daemon installed within that. All we have is the CLI binary placed there. And what we have done is we have mounted the var run docker.sock Unix socket file of the host machine's Docker installation. So now any commands sent to that Docker CLI binary are simply being relayed to the host machine's Docker daemon. So that is fantastic for us, because what happens is that we don't need privilege mode anymore. So from a security standpoint, that's great. And then we have a single union file system image layer cache. So the first time that somebody has downloaded a file layer, say containing the JDK7, no other job is going to download that layer again. They'll just reuse the Docker cache to do whatever building that it wants to do. And then any redundant network and disk I/O, that is completely eliminated. Those hundreds of megabytes that I was downloading every time, that's gone. Now the only, I would say, it depends what kind of trade-offs you want to make. So we made this trade-off, it was fine with us, is that there's a lack of isolation as far as the Docker image layers were concerned. So what that means is that there's a single point where you're going for everything. That's a single point of failure. Okay, so everything that we discussed, by the way, I think we went through our slides a little too quickly, but everything is available in much, much more detail on the eBay Tech blog. We have a couple of articles where we published, we have a Vagrant setup that actually, with screenshots and everything, where you can go and actually see how we ran through this entire process, and we have a working POC. So feel free to go there, and we've also linked to the Apache Mesos project. There's the Jenkins Mesos plugin, and of course Docker, and the Marathon framework. So that's it for me. I think your question is, whenever you want to make any configuration change in Jenkins, how do we achieve that, right? So whenever we bring up our Jenkins instance, we have a base template that we offer to the team that has all the plugins, Fortify and whatnot, everything pre-installed. Now, usually developers don't make a change, because that is, once you can easily go in Jenkins and edit the configuration, but ideally, since we have an established process, there's some team you have to go to and tell them to make that change persistent, that this is how I build my jobs. So we have an approval process. Usually, it's not standard practice to go and just change around configs whenever you want. You can, and there's always a place where you can set your job build scripts. That's saved within the Jenkins master. So those kind of changes you can do, but I don't think you can change anything major beyond that.
So the question was, were we using Mesos before Docker? The answer is yes. I mean, we started exploring Mesos before we were using Docker. But since we were using, on the slaves, we have to run these different types of workloads. And each workload has different requirements for dependencies and stuff like that. So it made sense to use Docker so that the process runs inside Docker container, and then you get your dependencies in a reproducible fashion. So did that answer your question? Okay. That's a good question. So the question is there an equivalent in the Yarn world for this? The answer is unfortunately no. Or the answer is partially yes. The biggest challenge with Yarn today is it doesn't support ports as a resource, and when you want to run multiple servers or application servers on a slave, and if they all listen on same ports, you will run into issues. What Mesos does is it also keeps track of ports as a resource in addition to CPUs and memories and disk. So when you get a resource, I mean an offer from Mesos, you also get ports as offers. And then when you bring up your process, you can allot ports dynamically. So that makes it really easy for Mesos to do it. Also, Mesos is a two-level scheduler, which makes things easier. I mean, we can talk about it offline.
Well, as I mentioned in the slide, that was a oh, sorry, I'll repeat your question. So your question was that by mounting the var run docker.sock file, we are violating security in some way similar to how we use privilege mode for Docker. So privilege mode is a much bigger bucket. You can do a whole lot more versus by just mounting the Docker socket. all you're doing is communicating with the Docker daemon. All you can do is a Docker pull, push, build, and that's it, really. There's not much more you can do on the host beyond that, and that too, you're just communicating with Docker. So I'd say that's a trade-off that we were fine with, because that's the only part where we're compromising on the whole isolation part. Yeah, so to answer your question, you were asking how the Jenkins job builds a Docker image. So yeah, basically every application will have a Docker file. What we're doing is we're basically executing your standard Docker build -t followed by your registry address, your namespace, your version, and eventually we hope we'll have a Jenkins plugin to actually abstract all of this out. So, so that way the developer won't have to even bother with any of this. So this can be just another Jenkins build step. Yeah. So your question was, how do we build the Docker file, and how do we build a Docker file? How do we build the application war file deliverable? How do we merge the two before pushing it into a Docker registry, right? So that's exactly how it happens. So what your Jenkins job will do is it will first, in case of a Java app, it will first do a Maven build outside before building that Docker file. It will first do the Maven build, generate that war file, because that Docker container within which it's running already has cached everything, JDK, Maven, everything that it needs. We're not downloading anything, we're not using the host Java installation. We already have everything in that Docker container. So it quickly runs a Maven build, it generates a war file, then it starts building a Docker file. We use an add instruction to just shove that war file into the Docker file, into whatever Tomcat location. So that Docker image that you're building from the Docker file already has Tomcat installed, so no downloading there.
Are those separate Jenkins jobs?
No, one Jenkins job, exactly. So that's what makes it so good. Yeah, so your question was, how are we downloading all the Maven dependencies? Are we baking it into the Docker image, or are we just downloading every time? So we leave that option open to the developer, because some developers may really not want to download. They might want to have a base image that caches all of them already. So that's outside of kind of our area of expertise. We have other teams that handle the Maven building and all those artifacts. So we leave it up to them. Either way, they can either bake it into their images, or they can download it on the fly every time. It will just take longer if they download it every time. So. Okay, I think if no more questions, I think that's it. We're good. Thank you.